soft collinear effective theory, or SCET for short, is an effective theory for soft and collinear infrared physics, and therefore it's an effective field theory for collider physics. So EFT So you learned about in Fabio's lecture why the soft and collinear limits are like very important limits of understanding collider physics. And so that, is the infrared limit that is important for processes at colliders, which typically we think of as hard collisions. There's some scale that's set by the hard collision. That's the high scale. And as you saw in Fabio's description of the shower, that was this Q-squared scale he was talking about. And then there was evolution to infrared scales. And that's where kind of the effective theory would be applicable. So this effective field theory can be used for a lot of different processes, because at colliders we have a lot of different processes. We have E plus E minus collisions producing jets. We have E plus E minus collisions producing a W. We have EP collisions, deep inelastic scattering, that could produce hadrons or jets. We have PP collisions that could produce a Higgs boson, a W, a pair of photons, lots of different things. So we'll see why sort of these things come out of this effective theory. And in general, it's also useful for other things. And at the end of my lectures, I have a long laundry list, which I probably won't write on the board, but I've posted my lecture notes, so you can have a look at it. So the basic idea is kind of what we've been talking about. We have QCD. This is the mother theory in this case, and it describes the physics at all scales, in particular also this hard scale of the hard process. And then we have from it an infrared theory, and that is going to be SCET. And that theory is designed to describe the infrared parts of QCD. So that could be lambda QCD, of course, that's in the infrared. And more commonly, perturbatively, there's IR scales. There could be some off-shell momentum, as you saw in this example with the Sudakov form factor, that are scales that are much less than Q squared. This is like the Q0 squared that you were just hearing about in the previous lecture. So it's a top-down effective field theory. We can match from QCD onto SCET. If I really wanted to describe kind of all the steps to you, it would take more than one lecture. So we're going to go through things. You've seen sort of examples of how things work. We'll discuss kind of the key things in these lectures. So one of the key things, of course, is the degrees of freedom, D.O.F. What are the degrees of freedom of this effective field theory? And to describe that to you, I'm going to focus my lectures on a particular example, which is E plus E minus to 2 jets. And we'll see from this example sort of how the degrees of freedom come about, and we can then generalize our understanding of why those degrees of freedom are relevant for a much broader class of processes, but let's just focus on this one. So how does this happen? Well, we have an electron-positron collision at a collider, and let's just say it produces a virtual photon, and at lowest order, the virtual photon couples to a quark and an antiquark, and then the quark and the antiquark go through this process of showering, and they could produce a jet, okay? But this is the lowest order Feynman diagram. In this Feynman diagram, there's some momentum of the virtual photon, and Q squared is just this little Q squared. So that's the energy of the collision. So what does the jet look like? Well, we were just looking at processes in the last lecture of what the jet looks like. So there's this process of splitting, right? And as you heard about, this process of splitting is enhanced in the collinear limit, meaning the small angle limit. There's logs associated to the collinear limit that enhance the splitting in the forward direction. And so we have this spray of radiation that forms a jet from that enhancement of collinear radiation. So there's going to be some jets formed from this process. In general, there's some direction of the jet. I'll call it n hat. So we have collimated radiation about some direction. Now the energy of the jet is like the energy of the progenitor of the jet, so that's like half the center of mass energy of the collision. So the energy of the jet is large. E jet is at this Q scale. Let me just say it's sim Q. So the jet has a large energy, but the transverse spread of the radiation is smaller, and that's going to lead us to our understanding of what we're expanding in this problem. It's going to be the transverse momentum of the particles in the jet relative to its energy. But in order to do that in a kind of systematic way, it's convenient to set up a nice coordinate system. Okay, and the nice coordinate system is a light cone coordinate system where we align things with the jet axis. So this jet is going in this direction, n hat. So let me define a 4 vector, which is 1 comma n hat. When I have light cone coordinates, I need a orthogonal, or a vector that's in the orthogonal direction, which will be 1 minus n hat. And these n squared is 0, and so is n bar squared. And in my normalization convention, n dot n bar is 2. So these are just some basis vectors like x, y, z, but we're using light cone here. So with those basis vectors, I can take any 4 vector, could be momentum, could be any 4 vector. I can write it out in components. And there's this pesky factor of 2 to keep track of, but that's, you have to deal with either 2's or root 2's. I prefer 2's over root 2's, so this is why I use this normalization convention. So rather than time x, y, z, we have what are called a minus momenta, p minus, a plus momenta, p plus, and then 2 perpendicular components, which I could call p perp 1 and p perp 2 if I wanted to give names to them. Okay. So these are a nice set of coordinates, and for reasons that you'll see. Let me also square the p. When I square the p, it's not like Euclidean coordinates. When you square p Euclidean, you get p0 squared minus px squared minus py squared minus pz squared. Here, when you square this term, n squared is 0. And when you square this term, n bar squared is 0. But the cross term is not 0. And so what you're actually getting is n bar dot p, n dot p. And then this last component behaves like Euclidean, so it just gets p perp squared. Of course, that's kind of a Minkowski notation. This is actually a negative of some vector p perp squared. So this is how light cone coordinates work. And we'll see that they're very nice coordinates for describing, for example, the collinear limit of QCD that's related to the shower. Okay, that's why I'm introducing them. So let's start talking about the particles in the shower, and we'll just talk about them one by one. So let's imagine that there's just one massless particle. Okay, well, if it's massless, its p is squared is 0. It has some large momenta, and it's in the direction of the jet. If there's only one, then it is the jet, kind of. So we can just say that its p mu would be m bar dot p n over 2. N over 2 is a 4 vector that squares to 0, right? And it has a 3 direction in the direction of the jet. So we know it should be proportional to n mu. The component in front is this n bar dot p. That would be the energy of the jet, which is order q. So we already kind of see why these coordinates are nice, like things are traveling along a light cone. If they're just one particle, it's this direction. All right, well, the real power comes when you consider more than one. So let's consider 2. So in 2, we have, say, a quark splitting to a quark and a gluon. And then I'll just call them 1 and 2. And we can decompose the momenta of 1 and 2 in this basis. So pi mu, the momenta of 1 or 2, is n bar dot pi, common n over 2, n dot pi, common n bar over 2, and then the perp component of pi. Okay, just writing it out, y is 1 or 2. So what do we expect for the size of those momenta? This is now I have a set of coordinates that I can sort of talk more explicitly about what I said in words over here. Well, when this splitting happens, this was the z in Fabio's lecture, when the splitting happens in the collinear limit, you could have z of order 1, so each of them could take, for example, half the energy. And in that situation, these n bar dot p i's are both large. They're some fraction of the original energy of the jet, q. Okay, up here, n bar dot p could equal q. Maybe I should have written that. In this first case. So there's only one particle. It carries all of q. Now there's two particles. They each carry a fraction of q, but they're order q in our counting, power counting sense. But the thing is, because they're collinear, that means that the transverse momentum is smaller. So the fact that they're collimated is the statement that the pi perp, whatever it may be, is much less than q. And that's the statement of collimation, that there's not a lot of transverse spread. And so what we say is that the pi perp is of order something that we define to be much less than q. Let's just say that the pi perp is of order q times a small parameter lambda. So we define a small parameter that's of order the transverse momentum. And this is the parameter we're going to do our power counting in. So if you like, it's like transverse momentum over energy, transverse momentum over this large light component. So we want to set up an effective field theory that expands in this lambda. Now, on shell, if I have pi squared is 0 for the final state particles, then you can look at this formula for p squared up there, set it to 0, and you see that n dot p is equal to p perp squared as a vector divided by m bar dot p. So this is just how the on-shell condition looks in these coordinates. And we have a power counting for p perp squared, we have a power counting for m bar dot p, so we inherit a power counting for n dot p. Okay, it's q lambda squared divided by q, so it's q lambda squared. And if you keep going, you know, the shower produces more and more particles. We could have, instead of just 2, we could have k. Okay, we could do 3, 4, 5, 6. Nothing changes. So we've already kind of derived the information that we need just by considering 2. So we get the sort of same information by considering more particles. It's not changing what I just told you. And so we have a scaling for what we call a collinear momentum, a momentum that's collimated close, not exactly equal, but close to some direction. So collinear, or we might say n-collinear, because it does depend on the direction we're expanding about, is a scaling for a momenta, which I can write like this as sort of a shorthand. In the plus, minus, and perp components, in the plus, that's this n dot p, that's of order lambda squared. So I'm using this shorthand of plus and minus up there. In the minus, that's the n bar dot p, that's of order q. So I just say it has no power of lambda, just 1 times q. And then in the perp, it's q times lambda, so I say the perp is of order lambda. So we call that a collinear scaling for a momenta. And in this effective field theory, we want to describe soft and collinear degrees of freedom. So we're going to need fields for particles that have collinear scaling of momenta. So with this scaling, I should have maybe left more room. we're going to have some quark fields as well as some gluon fields. I'm putting a subscript n on them. This is kind of like the V that we put on as a subscript in HQET. So this is quark, a quark field, and this is a gluon field. So these are going to be fields which have momenta that scale in this manner. They excite fluctuations that have momenta that are of that type. So far, so good. Okay. Well, you might say the next thing I should talk about is soft, but before I talk about soft, let me remind you that we want to talk about two jets, and so far I only talked about one. So let's talk about the other one. So we're interested in a process that involves two jets. So let's extend this discussion to having two jets. So we have this virtual photon, and it produced this quark pair, and then there is a spray of radiation in each of them doing its thing, and we had two jets, one up here and one down there in this picture. And each one of these kind of will have a jet direction. I could call this one N1 hat, I could call this one N2 hat, and then I could repeat what I just told you for each one, right? So the story kind of repeats independently for each direction. And in this case, I would define, if I use this notation, kind of an N1 and N1 bar, and I could go through the decomposition of momenta in terms of N1 and N1 bar. And down here, I would take N2 and N2 bar as a good coordinate system and repeat the story for that. And then I would come to the same conclusion that I did over here, just with sort of slightly different basis vectors. And this way of thinking extends beyond two jets. I could add a third, I'd have an N3 and an N3 bar, etc. I could do as many jets as I want. For two jets, I only need this. And that's how the story would extend. So I'd have some N1, AN1 fields that have momenta close to this jet direction, and I'd have some N2, AN2 fields for momenta close to this direction. And we just saw something that's kind of weird. That is, we have two different types of quarks, and we have two different types of gluons. The reason that we have two different types of quarks and two different types of gluons is because the kinematics is very different. These are different regions of phase space, and the power counting of these fields is quite different. They have large and small components that are quite different. And because of the fact that the power counting is very important, we're forced, in order to have a good power counting, to have two quarks in this process and two gluon fields in this process. Now, there's a lot of indices to keep track of: N1, N1 bar, N2, N2 bar. So what people do for this process is work in a particular frame that makes things a lot easier. And that's the center of mass frame. If I go to the center of mass frame, which anyway is the lab frame for an E plus E minus collider, where an electron and positron have the same energy, if I go to that frame, then the jets are back to back. So far, we haven't really specified to a frame, but let's go to this frame. It makes the picture a little simpler, and it makes the notation a little simpler. Let me draw it over here since I want to. Oh, I have another board up here. Let me draw it up here. So in this frame, the radiation on each side is in a kind of back-to-back configuration. So one jet this way, one jet this way. Okay. And I have equal amount of energy in each side. That's the center of mass frame. So in this frame, why is it easier? Well, I could say N, this is some axis, N hat, and I could say N, we could say N1 is just N, which is 1 comma N hat. Well, this axis here is minus N hat, right? And here n1 bar, which is n bar, which is 1 comma minus n hat. Well, that serves as a good basis vector here for n2. And n2 bar is then just n. So I reduce things back to just talking about n's and n bars in this particular frame. And so the fields would be c sub n, a sub n, and c sub n bar, a sub n bar. And that's a little simpler than having n1, n2, n1 bar, n2 bar. Does that make sense? Okay, so just kind of some notation. So let's talk about, let me just write one more thing. So we have a set of fields, and then we had how their plus, minus, and perp momenta scale. And in this case, I can make it all in one nice little tidy chart. What's happening for the Cn bar and the An bar is I'm just flipping plus and minus, right? So transverse means the same. It's transverse to this axis n hat of the jets. And plus and minus switch roles. N's go to n bars. They just reverse. Okay, so that is kind of nice. It makes things simpler. All right, well, one other thing I have to deal with is that I said I wanted to describe for you, I wanted to describe E plus E minus to 2 jets. And so somehow I have to forbid there to be 3 jets, right? If I was describing a process where there could be 3 jets, then I would need another direction if I knew there was 3 jets. So what am I going to do to make sure I only have 2? I'm going to have to make some measurement of something. Eventually, we're going to calculate some cross-section that's differential in something. So how do I get rid of greater than or equal to 3 jets? So what I can do is the following. We have this nice picture. Let me measure something that's kind of intuitive and simple to think about as follows. Let me define it as follows. We had this axis on the jets. Let me define a perpendicular plane to that axis. So this is perpendicular to that n-axis. These are my ability to draw in 3-dimension skills. I guess this is behind the axis. Okay, so this is, we have one jet over there, and this is the plane. Okay. And then I can say, oh, all the particles in this hemisphere, it's half of the universe, it's half of 3-dimensional space, hemisphere A and hemisphere B, I can make independent measurements on A and B. So let's measure what's called hemisphere masses, defined in that way. I take an invariant mass defined by taking all the particles that are in A, adding up their 4 vectors and squaring it, and then I do the same thing for B. Okay, so those are 2 observables. And they tell me something about how much invariant mass is in each of the 2 sides. They're telling me something about the particles on the 2 sides. And my claim is that if A and B, if these masses squared, either, actually both of them, so MA squared is taken to be much less than Q squared, and MB squared is taken to be much less than Q squared. If I demand that these masses are small, that's a way of constraining the radiation and forcing it to be collinear. And it's because of energy conservation, it's going to be collinear about this particular direction and not some other direction. If I had 2 jets in this hemisphere, I would not end up with a small mass. That's the statement. So this kind of restriction of small invariant mass is going to eliminate 3 and higher jets. So let me draw a picture to explain. So we have our hemisphere A, and we imagine that we don't have this configuration, but we have maybe a configuration with 2 jets. I'll call them, I don't know, 1 and 3. Maybe the jet on the other side is called 2. So let's imagine that we have this. We want to see that it's ruled out, right? Well, in this case, I would have, even if I just had one particle, I'd have in each of these jets, I'd have P1 plus P3 squared is giving the mass of hemisphere A, right? So the mass of hemisphere A would be like adding up all the momenta in this, all the momenta in this. It doesn't care. They're all in this hemisphere A, so I add them up. And there's a term in this that's of order P1 dot P3. But both of these things have a large energy along their axis, right? This one has a large energy along the N1 direction. This has a large energy along the N3 direction. So when I dot P1 and P3, there's nothing small about it. I just get that large energy component from each of them. And the answer is therefore of order Q squared, the energy of each, times the angle between, but the angle between is big. So there's some 1 minus cos, but that's big. So this is of order Q squared, and therefore is eliminated by these types of conditions. So this is schematically like E1, E3, 1 minus cos, theta 1, 3. This is order 1. Each of these is order Q, so this is Q squared. Okay, so that's how I can eliminate 3 jets. Of course, I had 4 jets, 5 jets, any more jets, also eliminated. So measuring small invariant masses like this guarantees that I have a dijet configuration. Okay, and then I don't have to add any more fields beyond these 2 that I had for the linear directions. You could also ask, what happens if 1 and 3 here became collinear? What if 1 and 3, what if these 2 jets came really close together? Then it should sort of merge back into this picture over here, right? If 1 and 3 come close enough, I should just call it a single jet, not 2 separate jets. So if 1 and 3 are n collinear, i.e. the scaling of the momenta P1 and P3 are n collinear, then the angle gets small, and the 1 minus cos theta provides additional powers of lambda. So in this case, P1n plus P3n squared is of order P1n dot P3n. And because of the extra power of theta 1, 3 and theta 1, 3 going small, you're getting something that's scaling like E1, E3, basically theta 1, 3 squared, and this is providing a lambda squared, the angles of order lambda. So you get Q squared, lambda squared in this case, and that's small. Okay, so then it's sort of, it's just those 1 and 3 are then just constituents of the same jet in that case. So that's how the 2 are distinguished. From this little calculation, you can answer how small should MA squared and MB squared be. MA squared over Q squared. From that calculation, it should be of order lambda squared. And I'll do the same for MB squared over Q squared. So we're just going to take both of these to be small by an amount lambda squared, which is our power expansion parameter. So kind of constraining transverse direction of momenta, which is how I started out describing things, is also equivalent to constraining the invariant mass. And this is, in Fabio's lecture, you heard about like there's different ways of ordering the shower in terms of angles, in terms of invariant masses. This is just 2 different ways of talking about collinear particles in terms of invariant masses or in terms of transverse momentum related to angles. So it's the same type of thing. You can talk about it different ways. Okay, questions? Yep. Yeah, so I didn't really describe, but basically cos theta would be like a transverse momenta divided by z. And the z momentum is like plus minus, but the larger one wins. So the z is of order q. The transverse momentum was of order q lambda. Except this is sine theta, not cos theta. Yeah. And then so this is small. And that's what transverse over z is of order q, lambda divided by q, so just lambda. And then I expand for small theta, and that gives me theta of order lambda. Yep. Okay, what about soft? I mean, it's the soft collinear effective theory, not just the collinear effective theory. We've talked about collinear. What about soft? So the point is that even with these constraints on the invariant mass, we could still have soft particles contribute to the measurement. They're not ruled out. So what is a soft particle? A soft particle is not collimated. So it doesn't care about its, this decomposition that we made in terms of plus, minus, and perp. It's homogeneous in space and time. So it has the same scaling, lambda to some power, for each of plus, minus, and perp. It should be lambda to some power because we know the meaning of soft is that the overall energy is small. So we expect that alpha is a positive power in order to get small energy for this soft particle. But what exactly is the power alpha? Well, we have to do a little bit of work to figure that out. And that's constrained again by the measurement. So the way to think about it is, say I had a collinear particle, and then there was some soft emission, like that. Then if this is going to contribute to within my kind of constraint on the invariant masses, then it's constraining the sum of the PS and the PN. So Pn plus PS squared can't be too big. Otherwise, it would kind of fail for the same reason that the extra jet failed. Pn plus PS I can write out. And it turns out that there's a single component of that dominates, and then there's sort of smaller terms. The component that dominates is when I take the biggest part of Pn. Remember, there's a part of Pn that just was order 1, the energy part, which in light cone coordinates is this n bar dot Pn. All the components of PS are the same size, so this is a lambda squared. So this one wins. All the other ones are subleading, lambda cubed and higher. And so when I take the sum of these two, I see that I get something, that's lambda to the alpha. I haven't yet told you what alpha is, but I just kind of made a mistake and told you. So if this is going to contribute to the invariant mass spectrum, it should be of order lambda squared, because this is an invariant mass, so this should be some lambda squared q squared, and that tells me that I should take alpha equal to 2. So radiation with alpha equals 1, that would be like the jets. It would get eliminated by the constraint, the extra jet. But radiation with alpha equals 2 is perfectly allowed and fits within the constraint. So alpha equals 2 radiation is allowed and will affect the measurement of this observable. Sometimes this is called ultrasoft radiation because it's softer than alpha equals 1, and sometimes the alpha equals 1 matters. I'm not going to do that. I'm just going to call it soft. We're going to stick with this example for the lectures today. Okay, so now we have soft radiation as well with alpha equals 2 on top of our collinear radiation. And we can go back over here and add, some more fields for that. We're going to have quark fields and gluon fields with lambda squared scaling for the momenta. Okay, so this right-hand stuff is always the scaling. Sometimes we call this Pn, Pn bar, and P soft. A table like that is kind of like, not that intuitive. Let me instead draw a picture for you that makes it easier to keep track of what's going on here. So we'll keep the table, but I'll draw it as a picture. So a nice way of picturing this is to remember that since P perp squared is plus times minus, I don't really need to worry about perp. And so I can draw in 2 dimensions, which I chose to be plus and minus, where these different momentum degrees of freedom live. And they live in some places, which are these dots. So the n-collinear degrees of freedom have a minus momentum that's of order q and a plus momentum that's of order q lambda squared. So that's why they live here in momentum space. The n-bar collinear momenta live over here, kind of the mirror, where they have plus momentum of order q and minus momentum of order q lambda squared. And then the soft ones that we were talking about lived here, where both components of order q lambda squared. Okay, so we're setting up a field theory that describes sort of these dots, these regions. We're doing kinematic expansions around those dots. The fields, of course, don't live at a single point, but they live in a region. But we're expanding in these different regions in order to describe the infrared. The infrared is small momenta. So if you like, in this picture, the infrared is the axis. That's 0 momenta, or some component of momenta is 0. We can't just get away with 0 homogeneously in the problem because there's angles in the problem. Jets go out at some particular direction that corresponds to, and then angles about that direction are important, and that's what leads to the whole story of having these components of momenta. We need to sort of have this part of the axis too. That's an infrared region, and we need a collinear degrees of freedom to describe that. Likewise over here, and then homogeneously we have this soft possibility as well. And so we're kind of giving full coverage of both axes with these degrees of freedom, where 1 degree of freedom wouldn't work because of the power counting being different. Okay, so this is an example of soft collinear effective theory. If you ask kind of what am I integrating out, well, there's something out here where both components would be big. And this would be hard. So that's what's being integrated out of the theory, and I'm only keeping the infrared degrees of freedom. In terms of thinking about invariant masses, which is sort of how we were describing things, invariant masses are pluses times minuses. So a fixed invariant mass corresponds in this picture to a hyperbola. So I drew this line, which is supposed to be a hyperbola, through this dot, and that hyperbola has p squared of order q squared. There's also a hyperbola going through these, and this hyperbola would have p squared of order q squared times lambda squared. Okay, if I square one of these here, I get plus times minus, that's order lambda squared, or I get perp squared, that's order lambda squared. So this is order q squared lambda squared. And then this one down here, if I square it, well, it gives lambda 4, so it lives on a different hyperbola. Q squared lambda 4. So in the usual way we talk about effective field theory, we would just be thinking about the hyperbolas. We'd be thinking about the invariant mass of particles. Is it big? Is it small? Sometimes we say energy. Invariant mass is Lorentz invariant, so it's a nicer choice. Sometimes we kind of are a little bit sloppy, say high energy, low energy. We could say high invariant mass, low invariant mass. We would just think about the hyperbolas. That's not enough here because of the angles in the problem. We need to have this 2-dimensional picture to really distinguish things. You see that Cn and Cn bar, the 2 jets, live on the same hyperbola, and that's not distinguishing them. One is going that way, one is going that way. Invariant mass doesn't know that, but the angles do. Okay, and the angles are represented in here by the large plus or large minus components. You could worry that maybe, we've made some frame choice and then we do some analysis and then things are going to depend on that frame choice, which was the center of mass frame. And the answer is that they don't. And the reason that they don't is that the important part of this picture is not so much that I chose the center of mass frame, but relative scaling between things. That's what's important in the picture. The collinear N has a much bigger minus momentum than the soft. This being bigger than that is a frame-independent statement. If I boost the minus momenta happen to boost multiplicatively, I change both of them by the same amount. It's still the same statement that the minus momentum of this is much bigger than that if I go to a different frame. Okay, so it's the relative scaling of things in this picture that's important. And we also of course have p squared, which is Lorentz invariant, separation of the modes. So this frame is convenient, but it's sort of, in the end, it's like we picked a frame and we picked a gauge, we did the calculation, it's gauge invariant, similar type of thing. Okay. That's what the degrees of freedom are. That's most of the work, actually. Well, maybe. Let me talk about the power counting. We've already kind of set up some power counting, like the momenta being of this size is telling us how big derivatives on the fields will be. But how big are the fields themselves? The fields, of course, in an effective field theory have a power counting, right? And it's not in dimensions. Sorry. It's one of those cases that's like the non-relativistic EFT that we talked about, where things are a little more complicated. A fermion field in this theory would have dimension 3/2, but in a power counting, it has only dimension 1, i.e. it counts like a single power of lambda. And the gluon field is even stranger. The gluon field's power counting isn't even homogeneous. So in plus, minus, and perp, the components of the gluon, the collinear gluon, have different scaling. Plus is order lambda squared, minus is order 1, and perp is order lambda. The second thing that I just told you is actually easier to understand than the first, so we'll start with the second thing, with the gluons. So why might this be reasonable? Well, remember that if it's going to be some gauge theory, that momenta and gauge fields go together. They go into a covariant derivative in the gauge theory, right? So you want to have some covariant derivative, I and d, which is some I partial. I'll put a subscript n on it to indicate that the derivatives are supposed to be of the size of collinear momenta. And then there should be some gauge field, A and mu. And if they're not the same size, I can't put them together into a covariant derivative, and I can't define it as a gauge theory. So they better be the same size. And yes, they're the same size. So I could derive that for you, but I think intuitively, the fact that it has to come out this way, if it's going to make sense as a gauge theory, is enough. So I won't derive that for you. You could derive it kind of by deriving the power counting. Instead, I'll just focus on the fermion case, which is a little less intuitive, and you'll see how I derive it for the fermion case, and then you could go and do the same thing for the gluon. Okay. So how do I derive this for the fermion? Well, I haven't told you what the Lagrangian is. If we had worked out the Lagrangian, you could look at the Lagrangian like we did in the non-relativistic EFT. If I knew what sort of my dispersion relation was going to be, I knew what the free theory looked like, then I could just use that, go through, normalize the kinetic term. I know how much d4x scales. Same procedure would give me the right answer. Since we haven't done that, let me do it a different way. It's always good to be flexible in life. Let's do it at the level of the propagator. Propagator in this theory, whatever the theory may be, should be a time order product of a Cassi bar from 0 to x, vacuum expectation value. That should be the propagator. And what that should be is some small lambda expansion of the full theory propagator. Right? This is the full theory propagator for a fermion. This is supposed to be the collinear limit of that. And you can write out the different components of this. There's a large component, n bar dot p, and then the p squared plus I0 is actually the same size. So there's no expansion there. And the reason why that's true, if I look at this formula again, is that this was order 1, and this is order lambda squared, and then this is order lambda, and there's 2 of them squared. So the 2 parts of it are the same size. There's no expansion. So I keep the full p squared. In the numerator, I could simplify things and just look at this n bar.p, which is order lambda 0, or order 1. P squared is order lambda squared, so this whole right-hand side is order lambda minus 2. Okay? P squared is of order lambda squared, so this 1 over p squared is order lambda minus 2. On the right, I need a power counting for d for x. Well, it's just the product of these things, 1 lambda squared and 1 lambda for each p. It's an x instead of a p, so this counts as lambda minus 4. The phase, while p's and x's are being put in inverse proportion, this is order 1. We're keeping the full phase. We're not doing any expansion of the phase. And now I know everything except for the power counting of Cassi. And you can see that I have to assign each of these to be a lambda to make things balance, right? And that's giving this answer. So that's kind of doing the same thing as using the free theory, but doing it at a propagator level rather than Lagrangian level. It's a free propagator. Okay, so this is the power counting. We have fields that scale like this. We have fields that scale like that. We could repeat the whole story for the n bar linear fields. It's the same thing, just switch n and n bar. I'll tell you how the soft fields scale momentarily. There's one other little thing that's a sort of little tidbit, which I'll just tell you. The fact that you got this n slash here when you did the expansion of p slash has some implications. And there's actually something that people call good components. This goes way back in the literature. Even predates QCD, I think, if I remember. So there's some projection relation that this field obeys, and it can be written, like we had this PV when we were talking about HQT. Here the projection relation looks like this. And these are called good fermion components in the old literature. And they are the components that are in a high energy collision. If you look at the form of the spinner and you expand with small p plus and large p minus, you end up with spinners that would obey this projection type relation. So I don't really want to spend much time going into that. I just present it to you as a fact. What about the soft? Well, in the soft case, we have the gauge field, and it's going to go like lambda squared, lambda squared, lambda squared, kind of by the same argument that it should scale the same way as the soft momenta. So that's pretty quick. And then we could go through and figure out how the soft fermion scales, and it ends up being lambda cubed. And I leave it as an exercise for you to figure out why that is. But you could make a similar argument to what we made over here. There wouldn't even be any expansion in that case. You'd have just assigned some power counting to the measure. You'd have the full p slash over p squared, and you could check. Okay. So this is the power counting of all the fields we need, the soft fields and the linear fields. We have the power counting. I kind of skipped over the symmetry. Remember that the three things we need for an EFT are power counting, symmetry, and the degrees of freedom. Let me briefly mention the symmetry. I've kind of alluded to it, but now I'll just list it. There are gauge symmetries in this EFT. There are 3 different types of gluon. So there are 3 different types of gauge symmetry. Even though it's the same gauge group, you have gauge symmetry in N, you have gauge symmetry in N bar, and you have gauge symmetry in soft. And those transformations can be done independently, meaning that if you are careful, you can set up an independent gauge for your N linear particles, N bar linear particles, and soft. Okay. There's a reparameterization invariance. I didn't really talk about this in the context of HQET, but the choice of N and N bar can be shifted, and there's sort of a symmetry associated with that. We briefly alluded to it in the question period when someone asked, right? So I don't want to go into it here because I didn't even go into it in the simpler case of HQET, but there's a reparameterization invariance also in this theory. And this is related to the, the fact that when we picked the N direction, we did something dramatic to Lorentz invariance because we picked a 4 vector that was a fixed thing, and it wasn't, we're using that 4-vector NR decomposition. So like you might worry, is it, all of a sudden frame dependence, Lorentz invariance destroyed? Lorentz invariance again gets restored in an expansion in lambda in this theory. And actually there's a symmetry at the order you're working that you could shift the vector a little bit and nothing should change. Anyway, so I just listed here for your knowledge. You could ask if there's any spin symmetries in this theory, and the answer is no. It's the same as QCD. So it's not like HQET where there's some new spin symmetry. All right. What is the Lagrangian of the theory? Well, it's a theory that has a power expansion in this lambda. And I like to divide the Lagrangian into two parts. The part that I call the dynamics of the collinear and soft particles themselves, and then a part that I call the hard interaction. Okay, there was this virtual photon, it produced our two jets. That's going to go in here. This was a hard interaction. That's going to be inside here. And then here, I'm going to have things where I have some n-collinear particle. Maybe it splits to a pair of n-collinear particles. That's dynamics of an n-collinear particle to begin with. Maybe it would be better if it was an n-collinear quark. So there's a split of the low energy degrees of freedom interacting with each other from sort of the fact that there was a hard interaction somewhere, usually only once in the amplitude, right? So dynamics in the EFT and the hard scattering are separated. They look as, they're just nice to separate. So let's first talk about the dynamical part. So the dynamical part itself separates. And I'm just going to write down for you kind of how it separates and then describe for you a little bit what the different parts are. So you can separate it into an n-collinear part, an n-bar collinear part, and a soft part. The soft part, if you just look at this Lagrangian, it's just QCD. It's QCD for soft fields. Everything's homogeneous. QCD was anyway scaleless before I go to a quantum level, it's scaleless. So this is just QCD for these fields. So nothing too special goes on here. So we just have a copy of QCD like that, just with soft fields. What about Ln? Okay, so let me see, I want to say some things. So you could check the power counting actually from this formula. Okay, so I told you I wouldn't do it, but you could check. Both of these things are lambda 8. The fermion lambda cubed times the lambda squared times the lambda cubed, that's lambda 8. G mu nu has a derivative and a field. Both of them give a lambda squared, so it's lambda 4 times lambda 4. And the measure, d4x, is lambda to the minus 2 times 4, so that's lambda to the minus 8. And so the product of these is order of 0, and that's how you see that the soft field Lagrangian is the same as leading power. So I could go through the full theory. I could do some exercise of integrating out and expanding. I'm not going to have time for that. So instead, I'm just going to derive for you the collinear Lagrangian based on our power counting. So if we look at the collinear Lagrangian, we can ask the question, what could it depend on? And that's an answerable question. Of course, it's going to depend on collinear fields, so these will be allowed. But let's ask kind of how it depends on in terms of covariant derivatives. So I'll look at it component by component. When I look at the n component, the derivatives are order lambda squared, and the gauge fields are both order lambda squared. The n dot an was order lambda squared, and the n dot a soft was order lambda squared. So it can depend on the sum like that. But when I look at the other components, for example, perp, then the an perp is bigger than the a soft. This is order lambda, this is order lambda. So I don't keep the a soft perp. And likewise, in the n bar, I don't keep the a soft dotted into n bar, just n. This is lambda to the 0, i.e. 1. So something got dropped. Just by a power counting perspective, I don't have couplings to two components of the soft field. I only have couplings to this one component in my Lagrangian. And the fact that there's only n.as, that leads to the Iaconal approximation for soft particles coupling to collinear particles. I have an extra E. For soft gauge fields coupling to a very energetic particles, whether they're coupling to energetic gluons or energetic quarks, it's only this n.as, and we just see that from the power counting. Okay. Now you could go through and figure out that you want ln0 to scale like lambda to the 4, since d4x scales like lambda to the minus 4. And then you could work out with these good components sort of what the form of the Lagrangian is, and I'll just tell you what it is. It's often written down just in terms of the good components because they're the ones that are produced at high energies. This n.d here includes the full thing there. And the n.d with the n on it only includes the collinear part. So the collinear quark Lagrangian for the good components looks like this. This is sometimes also known as the light cone quantized QCD Lagrangian. So people even use this Lagrangian prior to SET. What SET is really helping you deal with is how these different modes talk to each other. I tried to emphasize that in my little chart with the 4 dots. It's not like it's not improving the description of any one degree of freedom on its own. It's improving the description of the communication between the degrees of freedom. And the gluon, okay, plus the gluon part, and the gluon part has this similar property that only the n.a's come in. I'm not going to write the gluon part. ln bar is the same thing as ln. It's just you take ln and you swap in it an n bar. Okay, that's the leading power theory. Yep. Yeah. 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 Yeah, different d4x. Yeah. So it's a little bit tricky because there's soft momenta in the problem and there's collinear momenta in the problem, and they have different scaling. And so you have to keep track of that, and I'm not going to describe to you how. There's a couple of different ways, but it's a little complicated. But it's okay. It's the same lambda. Yeah, same lambda. Yeah. But there are different parts of the Lagrangian. You have an integral d4x for one part and a different integral d4x for the other part. It's like there's two different spacetimes. And it's like that one spacetime lives very far away from the other. And sometimes that physical picture helps. If you ask sort of what's going on with this soft field, it's a long wavelength mode. So let me give you the physical picture. This soft field is very long wavelength. It's got a very small p squared. And the collinear is, it's also small, but it's not as small as the soft. And so when you're like looking at the soft, when you're looking with soft gluons at the collinear, it sort of just sees the overall picture of what's going on with the collinear. It doesn't see kind of the details of the quantum fluctuations of the collinear into a different collinear. And that will come into some of the things I will tell you. So the fact that it's a much longer wavelength mode and the d4x scales differently is actually quite important, even if I'm not emphasizing it. So thank you for emphasizing it with your question. Okay, so what about the interactions? Well, we have some theories. We can think about the interactions and just kind of get some intuition of whether things make sense. Well, the soft gluon action was just the same as QCD, so all the things that would happen in QCD happen there. So if we have soft quarks, they can emit soft gluons. There's a triple gluon vertex, four gluon vertex, etc. I'm not going to write everything. The collinear Lagrangian is actually kind of similar. There's a 3-gluon vertex, a 4-gluon vertex. If it was just collinear particles, it would just be a copy of QCD written in a weird way. So there's nothing really that's getting dropped as far as the collinear interactions. I like to draw a little line through the collinear gluons to denote that they're different than the soft ones, because otherwise I'd have to use colors, and I don't have enough colors, so we'll do that. Where there's something interesting happen is when I talk about the interactions between them. So I could have an N collinear particle. Now I will try to use some color. Maybe I'll use blue. It doesn't show up that well. So this is soft coupling to two collinear gluons, or two collinear quarks coupling to soft, a soft gluon. So there's interactions like this, and again, there's an etc. And these gluons here would be this N.A soft component. The Lagrangian tells us that these are N.A's. That's the only one that happens at leading power. If it was a different component of the soft gluon trying to couple to the collinear, that would be subleading power, but not leading power. You see there's something else that I didn't write down, and that is couplings of N's to N bars. This Lagrangian doesn't allow N's and N bars to talk to each other. So that's kind of a prediction of the Lagrangian, that they don't talk to each other. So why don't they talk to each other? The reason that they don't talk to each other is because you can't add their momenta together and have something that remains inside the effective theory. So you don't have something, for example, with an N collinear gluon coupling to an N bar collinear gluon, because whatever came out of that, whether if it's a gluon, would be hard. It would have a large minus and a large plus, so it would have a large p squared, which is of order p plus times p minus. It would be of order q squared. We're integrating out such gluons when we construct the EFT. So in the dynamics of an N collinear gluon, it can never fluctuate into an N bar collinear gluon. This type of thing, this type of hard dynamics can only happen in one place, and that's at the hard collision. That's the place where there's hard dynamics. And at that hard collision, we integrate out such gluons. They're going to go into some Wilson coefficient of the theory. So this is kind of only in Wilson coefficients of the theory. And there's no Wilson coefficients in any of the leading power Lagrangians, because they're normalized again by kinetic terms and symmetries. So the only place that can really happen at leading power is in the hard Lagrangian. So let me talk about the hard Lagrangian. This depends on the process. The dynamics doesn't depend on the process. It just tells you how particles evolve in some process. You know, we have many different processes that involve producing an energetic particle becomes a jet, you know, independent of how it was produced. But how exactly it was produced depends on the process. So the E plus E minus to 2 jets is going to come in here. If I do E plus E minus to 2 jets, then I have in Q, I can think about it from QCD. In QCD, I'd have the vector current if I'm doing a virtual photon, which I am. So it would just be an operator like that. And what that's going to become in the effective theory is some C, okay, it's going to be some L hard 0, which is some C times some operator. And the operator, well, one of the quarks is going to be collinear in one direction, one of the quarks is going to be collinear in the other direction. So the operator, you can imagine, I leave some space, it has some Cn and some Cn bar. Okay, there'll be some Dirac structure in the middle. Let me just call it gamma. It's not too important for our discussion. And then there's actually something else that happens. And that is that there's some Wilson lines that show up in this operator. I call them W. So that's something new. There's some collinear Wilson lines. And I want to describe to you physically, not mathematically, well, a little bit mathematically why they show up, but mostly physically. The reason that let me define for you first what it is. So this is a path order exponential of gauge fields. And in this particular case, it's a path that goes from 0 to infinity. And for this Wn object, it's an an component n bar along the path n bar. So it's a line, and it's in the n bar it's in the n bar direction, and it allows the coupling of an gluons, but only the an minus component. The an minus component was order lambda to the 0, and so in fact, those order 1 gluons rearrange themselves into these Wilson lines in the theory. And you can trade them actually exactly for Wilson lines, but I don't want to write down the algebra of how you do that. So I want to explain for you why these Wilson lines are coming in. So if we go back to the process that we're talking about with virtual photon producing these, I put the n bar up here this time. If I think about attaching some n-collinear gluons to this process that I had, where this is n bar, remember that if n bar and n come together, it becomes hard, right? So in this type of picture, this would be hard. This is fine. This is sort of in the Lagrangian. This is just L0, Ln0. So is this vertex. But that propagator up at the top is that I colored red. It's not part of the Lagrangian. It's hard. I have to integrate it out. And it turns out that when I integrate out such things, I produce these Wilson lines. Okay, so that's like mathematically what's going on. That's how you could derive it from integrating out hard particles in the matching. Physically, what's going on? Physically, what's going on, you can think of from the symmetries that I vaguely told you that there was these different types of symmetries, including collinear symmetries in the n direction, collinear symmetries in the n bar direction. If I do a collinear gauge transformation in the n direction, the n bar fields don't change. So there's a mismatch, an imbalance from the gauge symmetry point of view. We had these two particles, they both carry color charge, but I do some type of gauge transformation. This one can change and this one can't. You know, how can that be? What balances it is this Wilson line. So this product is n-collinear gauge invariant. And the Wilson line, the reason physically what's happening is you can say as follows. When these n-collinear particles probe the color charge in this very different collinear direction, they don't see the details of what's going on again. What they see is just sort of the overall charge of those particles and the direction. Well, okay, they don't even really see the direction. But they just see some overall properties of those particles, and those properties are all captured by this Wilson line. So there's some expansions that are happening, and the approximations of this particle, how it sees the other jet, is all encoded in this Wilson line. The Wilson line does transform under a gauge n-collinear transformation, but the product doesn't. Okay? So that's kind of physically why there's these Wilson lines. I will pause because maybe there's a question. And then the same thing can be repeated with the n-bar collinear guys, and then there's sort of, again, I get on this side a similar story where I need this n-bar, Wn bar for the n-bar collinear fields in order to balance the gauge symmetries for that jet. And this seems like maybe it's special to this example, but it's generic actually, and when you do all sorts of examples, you're always getting this Wilson line. So every quark is dressed by a Wilson line. Every gluon field also gets dressed by an adjoint version of the Wilson line. And these are kind of the fundamental building blocks of the EFT. It's not just a quark field by itself, but a quark field times a Wilson line. because that allows you to put things together that are kind of in very different directions and describes how they couple to each other. There's a bit of a confusion with the notation. Okay, which I mentioned. It's Wn because it's n collinear fields, even though it's in the n bar direction. Sorry. It's a good notation, I claim. And the reason it's a good notation is because the n is general, but the n bar actually is free. If this had been an n1, if this had been an n2 jet and this had been an n1 jet, let's say this is an n jet, so I don't change too much notation. Say this is an n jet, but I don't call this n bar. It's not back to back. I call it n2. It would still be n bar. The coordinate system associated to this jet, it doesn't care about this jet, really. If this was a heavy particle and it wasn't even a jet, you'd still get the same formula. So it's really independent of what's going on here. All you care about is that there's something over there with color charge that doesn't transform under this gauge group. And you do the calculation for kind of anything over here, just generic thing, and you'll get this answer. Okay, so the notation is kind of awful, but meaningful, like purposeful. Okay. What else? Well, there's a Wilson coefficient, C. We can get the Wilson coefficient by doing matching calculations. It works the same way we did HQET. I'm not going to go through the details, but we would write down a loop diagram in the full theory. There could be wave function normalization, vertex. That would involve all regions of momentum space, including the hard one, the red one in my picture, right? Then I subtract the EFT. There's some loop diagrams in the EFT. There's actually loop diagrams involving n-collinear gluons and bar collinear gluons, soft gluons. That's removing from the full theory the infrared, and I'm left with a mismatch. The mismatch is in the ultraviolet, and I get some result for the Wilson coefficient. And so I'll just write down what the result is for the Wilson coefficient. It's a function of the hard scale, q squared, and at one loop, it's got an interesting structure. It's log squares of mu squared over q squared. But it's not just a single log, there's actually a double log, which is kind of interesting. Okay, there's also some number. -8 plus pi squared over 6. This is in the MS bar scheme. And then there'd be higher order corrections. This is actually known up to alpha cubed. Only write down the order alpha. So when we did the example before, we have a single log showing up in the Wilson coefficients. That's maybe expected. Here there's a double log. That's kind of interesting. The presence of that double log is related to the fact that of this Sudakov form factor, actually. It's related to the fact that in the infrared, there's two different types of logs that can show up. In Fabio's picture that he had this angular integral d theta and a 1 over 1 minus cos theta, and he had the dq0 over q0. There's a divergence that happens as q0 goes to 0. There's a divergence that happens as the angle goes to 0. Each of them produce a logarithm. That's why there's a double logarithm. And this, in general, this theory has double logarithms, and the resummation of logs is of double logarithms, Sudakov logarithms, not just a single log series in general. So another way of talking about this would be, as part of the matching calculation, I had to renormalize the EFT. And when I renormalized the EFT, there would be some anomalous dimension, right? As we've talked about. And the form of the anomalous dimension here, which I can write as writing, just like we did before, I can write the derivative of log c, right? And then the right-hand side is the anomalous dimension. And the one loop anomalous dimension that would come out of the same procedure that we used, you have some zc, you take the derivative of it, has a logarithm in it. So this is sort of what differs from the example that we had before. So there's a log of mu squared over minus q squared. It's kind of like, you take a derivative of this log squared, you get a single log. There it is. And the presence of that log is going to, when you solve this differential equation, give you a double log series. So leading log here corresponds to saying that c is like 1, and then alpha log squared, alpha squared log 4, da da da. You get one double log for each order in alpha. What matters in the end is sort of the mod squared of the c, so all the I pi's and its real result. And I'll just write for you, if you solve that differential equation, how it looks for this h, because this is something you saw earlier today. So it exponentiates. That's just the fact that it's d by d mu of log c. You integrate with single log, you get double log. There's some terms that come from the running of the coupling, which I'm sort of not writing, because I think this formula is more intuitive. We could solve the equation exactly like we did in the previous case, where we account for the running of the coupling. And that'll just, in this formula, include some dots. There's an infinite number of terms that come from the running coupling. They involve beta naught. The intuitive part is that there's this double log and it's exponentiated. And this is exactly the Sudakov form factor for the problem that we're talking about. Why is there a Sudakov form factor? Remember about the Sudakov form factor, which was this delta that Fabio was talking about. What was it physically? It was the probability of not radiating. Okay, you have some process and it doesn't radiate before some scale. So this thing is encoding the probability you produce something at mu q and it didn't radiate until you got to mu. Mu is where your effective theory lives. And at mu, you have radiation. We have soft and linear radiation. So you're allowed to radiate there, but until you get there, you don't have any radiation, and that's coming out of the renormalization group flow in this effective theory is reproducing that Sudakov form factor. It's forbidding there from being any radiation until you get down to the scale where you have the jet, and then of course there's lots of radiation. But we didn't have any radiation until we got to that scale. That's partly why we have 2 jets, not more jets. Okay. Okay, so I have a few things to tell you. So so we can use this effective field theory and we can derive what are called factorization theorems or factorization formulas that describe differential cross sections. And in this case of E plus E minus to 2 jets, I just want to give you a feeling for what that would look like. We've already factorized, in some sense, part of the problem because this Wilson coefficient contained the hard region of phase space, and it was factorized as a very simple product, C times O, from all the light stuff. But even in the light region, we still have collinear and soft stuff. The collinear stuff is fine because the n collinear stuff and the n bar collinear stuff, it didn't talk to each other. Okay, so it's already factored. The soft stuff was still coupling to each other, but it was coupling in a very particular way through this n component. And it turns out with a little work, which I think I will, in interest of time, not discuss, that you can decouple. So we can decouple the degrees of freedom in the EFT. N with n bar is already decoupled. It can only couple through the hard interaction so that the dynamical Lagrangian doesn't need to be manipulated. N with S can be decoupled And it actually can be done with a field redefinition on that Lagrangian. And when you do it, you produce some more Wilson lines, which I don't really have that much time to describe, but you get some soft Wilson lines. You can basically add up all those couplings and put them into another Wilson line. And then once you've done that, you end up with a dynamical Lagrangian that's completely decoupled after you kind of make a change of variable, where this is only n collinear. There's only a direct sum of pieces that are independent of each other. So only n bar, and only soft. The theory really splits itself into 3 independent pieces. Each one does its own thing, doesn't care about the other one. All the interactions between things have been taken into account, both through the hard interaction and through this step of getting soft Wilson lines. Okay. So if you want to know more about that, I'll refer you to my online lectures. But that's kind of nice, because that means that if the dynamical Lagrangian is the sum of 3 parts, the whole Hilbert space splits apart into direct products. And so if I want to factorize some process, I can really kind of get independent matrix elements, not kind of, I can really get independent matrix elements for the collinear and soft parts of the process. And that means when I go to do calculations, I can just calculate them completely independently and then put them together at the end. And that's factorization. I will tell you what the SCT operator looks like after this step, because it's sort of where things are still coupling. Okay, I think I made this the Wn, this the Wn bar. This is what happens after that field redefinition. You get no interactions here, and all the interactions go into a pair of Wilson lines that show up in this OSCT0. And then you can go from there, and you can derive for this doubly differential invariant mass a factorization theorem. Let me start with QCD. Okay, we should write down something that we can then write in terms of the effective theory. What would it look like in QCD? Well, the leptonic part of the problem you can do exactly. It's going to give you some leptonic tensor from your electron neutrino. And then the hadronic part of the problem, it would be, in this case, matrix elements of a hadronic current with some state x, right? It's a squared matrix element. One of the currents is at mu, and one of the currents is at 0. There's no hadrons in the initial state, so it's vacuum in, x out. And then the indices of these hadronic currents in the full theory are dotted into the L. And then I'm making a measurement. So there's some delta function that defines the measurement that I have to put in. This sum over x includes like integrals over the phase space of the variables x. And these delta functions are kind of just restricting that calculation of that phase space by fixing one of the variables in each hemisphere. So this is how it would look. In the effective theory, the J gets replaced by this O. The sum over x gets replaced by a sum over x of s, x of n, x of n bar. Things split apart. And you can factorize this by making a lambda expansion into some prefactor, which is just some number. This h that I was talking about over there, and then 2 more objects that are called jet function and soft function. There's 2 jets, so there's 2 jet functions. They're the same function, just evaluated with different arguments. And there's a soft function. The soft function describes the soft radiation. The jet function describes either the n-collinear radiation. So this is n, this is n bar, this is soft. And the fact that there's these independent functions is related to what I was telling you, that you've split the Hilbert space into separate parts. You can split the states x into a product state of x of n bar, x of s. So you really get independent matrix elements defining these functions, and they're matrix elements of field theory operators in our effective field theory, so we can, calculate them to some order in perturbation theory if they're perturbative, etc. So it's important to note is that we have not made an expansion in alpha. We've made an expansion in lambda, but this formula is to all orders in the strong coupling. There's no alpha S expansion. So usually we're used to like having to rely on perturbation theory. Here, we just relied on symmetries, properties just of the effective field theory, how it knows about how things talk to each other. We didn't have to rely on any coupling expansion. So this formula can be used at leading log, next leading log, next to next leading log. Current state of the art is next to next and next leading log. Okay, so you can go far with it. It sums logs, and if you sort of build a picture of what's going on, you have this hard function. You've got this, which I'll just say lives at q squared. You've got this invariant mass scale, ma squared and mb squared, and this jet functions live down at that scale, and then you have this s function, and it lives at ma squared, mb squared, all squared over q squared, sort of one step smaller. And then you can do the same type of thing that we've talked about, where you have some mu squared and you evolve the functions from their canonical scales to the common scale mu that they show up in the factorization. So you would do perturbation theory at the boundary, do some renormalization group evolution. This thing here is this thing here. So that one we described, right? So there's a UH, this is the UH, this thing here is the UH. I told you how it kind of looked, but there'd also be sort of a U that you need for the jet and for the soft if you want to do the full resummation. You have lambda QCD. I'm imagining it's down here somewhere. This picture of the EFT tells you sort of, if you ask the question, where is lambda QCD? It's in the formula. It didn't get dropped. If you ask where is lambda, remember it's non-perturbative, right? I never made a series expansion. So lambda QCD is in there. If you ask kind of what's the most important effects of the lambda QCD, it's in this S, because it's the thing closest to lambda QCD. So there's non-perturbative effects in the soft function. You could treat it perturbatively if you wanted to drop them. You could treat, and then you could do some kind of expansion, say in the ratio of this scale to that scale, to figure out the leading non-perturbative effects. They would be associated to soft particles hadronizing final state jets. And it turns out that to first order in some expansion, this over that, it can be described by a single parameter, analogous to our lambda 1 in HQET. In this case, it's called omega 1. Okay, so you can use sort of the power of EFT ideas to describe the physics of this situation. I don't have time to go to any more detail than that. I wanted to mention a few other things before we stop, so maybe I'll take questions about what we've just discussed and then go a little bit further. So this is E plus E minus to dijets given by two jet functions, one soft function and a hard function. That's the factorization theorem. Yep. Yeah, so H is the hard dynamics that it integrated out. H was the Wilson coefficient squared. So the Wilson coefficient contained all the hard physics. And in this particular process, these would be virtual corrections in the production process. So it would include, for example, a diagram like this, where the momenta going around in the loop is hard. That would all go into the Wilson coefficient. So this would be part of C. If the momentum was small, if it was linear or soft, it would have small invariant mass. The loop would be part of the EFT. If it's hard, that region of phase space gets integrated out, and that in the end goes into the Wilson coefficient. We usually don't calculate by doing like a loop diagram in the hard region, although sometimes you can get away with that. Usually we do the calculation by doing the full theory calculation, the effective theory calculation, and subtracting. But physically, this is sort of what's going on. There's a hard region of the full theory phase space that's not captured by the EFT, and it's going into the C. Yeah, and then it goes into the H because I square. I'm looking at amplitude squared in the cross section. Other questions? So one question you could ask is sort of how universal are the objects that are showing up? And it turns out that they're quite universal. This jet function will show up anytime you're looking at a jet that's inclusive enough. Sometimes it's called the inclusive jet function because we kind of specified a hemisphere, but we didn't really worry about like a jet boundary. If we had a jet boundary, like a radius for the jet, if it was an anti-KT jet, it would depend on some more stuff, like r, the jet radius. So there's an analog of this jet function that would depend on the jet radius for an anti-KT jet. Here we have a very like simple jet. It's like all the things on this side are, allowed to be part of the jet. It's constrained to still be collimated, so it's still a jet. But this inclusive jet function does show up actually in other processes, and you can even make it show up if you've got a PP to 5 jet event, if you measure the right thing. The soft function, it also shows up all the time. It's kind of a simple example of some object that has, so it is, trust me. So that's nice because like say you're doing a calculation, actually the H also shows up. So say you're doing a calculation of something different and somebody's gone ahead and calculated it, then you just reuse and recycle, right? So if somebody's calculated this thing out to 3 loops, which happens to be the case, then you just stick it into your calculation. You don't have to calculate it again. And that's kind of nice. So just like a parton distribution function is universal, here some perturbative objects, because of this factorization, are universal. And that's kind of makes things powerful because you can get further. Okay. Well, I wanted to briefly talk about a few more things, but just kind of very briefly, not in the kind of extensive way that we did about this example. But just to give you a feeling for sort of how things would work in other scenarios, right? We have this very particular example, E plus E minus the jets. We had no parton distribution function. So let me give you an example that would at least involve some parton distribution functions. Let's say we were doing the example of PP to X mu plus mu minus. This is Drell-Yan. I could replace the mu plus mu minus by a Higgs. Pretty much the whole what I'm about to tell you would go through the same way. This is a process that happens at the LHC. We measure extremely well. How would it look? Well, in this process, there's sort of one complication that didn't happen in our E plus E minus the dijet, and that is the following. So let me draw the process, and let me draw it as a squared matrix element. So these things here are protons. From the proton, I'm taking a quark. I'm colliding things, producing a virtual photon. It's kind of like the reverse of the jet process, right? And then there's some lepton pair, which are muons in my case. Okay, well, you could say, well, how do I set up the EFT for that? Well, the 2 protons are coming in back to back. Okay, we celebrate them center mass frame. So one of them can be n collinear, the other n bar collinear. Very natural. Fine. The additional complication is that in this x, we don't put any constraints on x. We want to be inclusive over x. And if we're inclusive over x, x itself could be in the hard region of phase space. So you're allowed to have some gluon that's hard in the problem, in the x. And that means when you want to integrate out the short distance physics, you have to do it at this amplitude squared level because you're going to have not just the virtual corrections that we were talking about in the other case, the H was purely virtual. You're going to have both virtual and real corrections that are in this hard region of phase space. You have to integrate them out all together. And when you do that integrating out, you're left with some object that looks like a four-quark operator after integrating out the red stuff. And the type of operator that it looks like, okay, there's also these same types of Wilson lines. I told you they were going to keep showing up. So yes, they keep showing up. Looks like this. So the Wilson lines are showing up again. And you're getting a pair of quark fields in the n direction, a pair of quark fields in the n bar direction. The matrix elements of those operators are parton distribution functions. So f I p of Cassi comma mu is a proton matrix element of Cassi n w n flavor index I n bar slash over 2. There might be some 1 over p minus somewhere. Actually, there's not. Well. And what about this Cassi? Well, this Cassi happens because you've got two quark fields here. You've got two objects. They're separately gauge invariant on their own. And so it makes sense to talk about them as things in the theory. And in particular, it makes sense to talk about the amount of momenta that each of those parts carry of the operator. And overall momentum conservation in the matrix element does not constrain anything but the sum. So it doesn't tell me how much is carried by this part of the operator or this part of the operator. And so there's a free variable, that split. And the free variable is this, Cassi. So there's a constraint, or if you like, there's a delta function. If I write it this way, it'd be some delta function that looks like, okay, some kind of momentum operator normalized by the momentum of this state that acts on this product of fields, picks out that momentum Cassi. And this really has kind of a parton model picture for what the PDF is. This is a parton. Okay, there's a Wilson line there because the parton model is just an approximation. This is truth. There's a quark field and a Wilson line. The momentum of that combination is a gauge invariant thing. It makes sense to talk about it. And this one gets fixed by the overall momentum conservation, so we don't need a separate label for it. And that's the quark momentum fraction Cassi inside the proton. So we normalize to the total proton momenta. Okay, so this is the matrix element of the PDF. It's sometimes, if you look it up in some book, as an operator definition written in position space, and this is the Fourier transform of the formula that you might find for the parton distribution function in a book. Okay, so that's how a PDF would show up in the process, and you would, in this process, the factorization would look like some hard function. There's some variables which are often written as XA. This is how I think Fabio called them X1 and X2. I called them XA and XB. And then you'd have these PDFs. Okay. This has indices I and J, and you sum over I and J. And the hard function would be Wilson coefficient coming from integrating out all that red stuff. So this is short distance. So you do a short distance calculation of partons to calculate that, and you could then tie it together with PDFs. That's how it would work from an effective field theory point of view. And the separation of the operator in the effective theory and the factorization scale, which we talked a little bit about, now you can kind of see why, right? Because like there's a separation between these operators. They gave the PDFs. And if you do a normalization group for this PDF, you get the DGLAP equation if you do a normalization group for these operators. Okay, so that generalizes a little bit our discussion. We're kind of out of time, so maybe I'll just make some final comments. I said that this combination try to write very little on the board. I said that this combination is generic, and so it's kind of behaving like a building block of the EFT. There's an analogous thing for a gluon. So this is sort of a gluon building block. And again, it's effectively a gluon attached to a Wilson line. It's like a G mu attached to a Wilson line. It has two components. So it's got the physical components, if you like, the transverse components. And when you build operators in EFT, you really just need this chi for the quark, the B for the collinear gluons, and then you need one more thing, which is P perp. And you can actually go to higher orders in the EFT beyond leading power just by using those three things together with some soft things. And you can build operators in higher powers of lambda and do expansion. It turns out that using all the symmetries in the equation of motion, that you just can get away with just those three. So it's not really super complicated. Okay, some calculations may get complicated, but at least conceptually thinking about what you have to include is not that complicated. Thinking how to dot the indices is complicated, but you can use spinor helicity, and there's some tricks to getting around that. I mentioned that I would tell you a little bit about, so kind of bottom line is that the EFT makes, it's not like mandatory at leading power. People have worked out factorization theorems with traditional methods for many years, but it makes things easier. And that's allowed people to go to new processes that what will be difficult, or processes with multiple scales. And working through the factorization in those cases, here we had an example that had 3 different scales, and if I counted MA and MB as separate, then it would be lots, even more than 3, right? And we were able to do it today, so it can't be that complicated. I mentioned to you at the beginning that I would kind of give you some feeling for why this is talked about a lot and why is it used a lot. And that's because collider physics describes a lot of the ways we talk about particle physics, right? It's a very crucial tool. And that means we've studied an immense amount of processes. We're interested in colliding things at high energy to probe short distances, but then what comes out? Well, it's standard model stuff. And that's described by this EFT. So just to give you a kind of a list, there are exclusive processes. Our examples here were kind of more inclusive, but you could have an exclusive process that just involves like a pion or a proton. And if that pion or proton was energetic enough, it would be collinear. It would have a transverse momentum of order lambda QCD, but so what? The effective field theory is non-perturbative. It can describe those things. So you can describe energetic hadrons. You don't have to just describe energetic jets. So you can use it for exclusive processes. You can use it for inclusive processes like the deep inelastic scattering, the Drell-Yan, W production, diboson production. There your factor is rising like the PDFs. If you put constraints on the X, make it into a jet, you're still good. You can still describe it. You'll get one of these jet functions. Okay, so you can make it less inclusive and still describe it. You could have a hadron inside your jet. Your jet might have an identified hadron. That you can do too. Jet processes, so you could have Higgs plus some fixed number of jets. That's very important experimentally, because experimentally you take the Higgs, you divide it into jet bins, because the background for Higgs plus 0 jets is very different from Higgs plus 1 jet, Higgs plus 2 jets. So you actually want to theoretically calculate Higgs plus some number of fixed jets, because experimentally that's used. And you can do that with this EFT. People have looked at jet substructure, so not just like the jet itself, but let's peer inside the jet. What's going on? Maybe inside the jet, you find 2 lobes of information, right? And that tells you, aha, it wasn't just coming, maybe it came from a W boson, and I found that out by seeing that inside the jet, it looked like 2 subjets. It was a very energetic W boson, so it looked like it sprayed its radiation all in one location, but if I look inside, and LHC has enough angular accuracy to do that, I see 2 lobes of radiation inside a single jet, and that tells me something about what's going on. So that's called jet substructure, and you can do jet substructure with a little bit of a more advanced version of this theory. You can do flavor physics. If you've got a B meson, it's very heavy. It decays to 2 pions. They're very light. They'll have a lot of energy. So there's examples like that. People are using it for small x physics, so the list keeps going. I think I'll just stop um, and take more questions. Yep. 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 Yeah, you still have the same scaling, so let me describe why. So let's say we have a very energetic pion, and it'll be produced at some point by two quarks that have the right quantum numbers, so maybe it's a U bar and a D. And then there can be some gluons, quark pairs, whatever, in the hadronization process of the pion. So originally there was some hard vertex that produced a U bar D, and then something happened and it became a hadron. And it's very energetic, so there's a direction associated to where the pion was found. And now you can ask about the scaling here, and it's exactly the same, lambda squared 1 lambda, but now the lambda is a different lambda. Now that in this case, you still have Q. It's a very energetic pion, so there's a very energetic minus direction. But if you ask about the transverse, this lambda times Q for the transverse momenta, what you know is that the size of the hadron is of order lambda QCD inverse. So the typical transverse momentum of the degrees of freedom that are hadronizing are of order lambda QCD. So the transverse momentum, the transverse spread is lambda QCD. So what you're expanding in here is lambda QCD over Q for this hadron. So it's the same collinear degrees of freedom, but just a different lambda choice. Yeah, so the soft won't be below lambda QCD, so that's a constraint. Yeah. You don't have, so like you couldn't have something scaling like lambda QCD squared over Q for the soft, because then it would be somehow outside of the hadron and that wouldn't make any sense. So the soft can at most be lambda QCD in all components. So it gets kind of frozen out there. That's sort of, and in my counting, that sort of makes it single power in lambda instead of 2. So this would be alpha equals 1 instead of 2. Yeah. 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 Yeah, not really. No. Yeah, I mean, it's really got a very different functional dependence, right? These things are variables and you need to track them. And that makes the calculation of this hard function harder than the one we did over there. The one we had over there had Q squared. Okay, there's also Q here, right? It's a little sloppy. There should be a Q, there should be a mu. So these variables, the Q and the mu, they're common, but there's 2 new variables, so you have to work. And there's different diagrams, right? As I said, there's the real radiation diagram. So maybe you can recycle your full theory. You can certainly recycle your full theory virtual diagram, but then you have to add the real radiation diagrams. Yeah, so what happened like in the other process is we sort of forbid final state radiation that was hard by our measurement of the invariant masses, and that's why there was like no third jet, et cetera. Here it's allowed. The virtual diagram, okay, it's a time reversed version of the E plus E minus the QQ bar, so I could recycle the virtual diagram at one loop. But the real emission diagram, I just have to calculate fresh, and that's where the non-trivial dependence on the variables is going to come from. Yeah.